So what we wanted to do in this final session is have a bit of an open discussion. As Munzer pointed out in the introduction, part of having a symposium was to gain some insights into how we should think about establishing statistics here at MIT, getting input from our colleagues who are at departments across the country already. And so one of the things we wanted to do here now was to have an open discussion of various sets of points. And so it'll be a bit of a structured discussion because we've put together some questions, and that we've given to our guests already. But I'm gonna start with a topic that structured but guided by what I want to talk about. No. But I'm going to start with a topic that we bantered around a little bit last night at dinner, and it's what the structure of the departments should be. And even out here just a few minutes ago, there were some very strong comments on that. At the moment, the way the new entity, at least the new Center for Statistics component, will be set up is it'll be a joint effort between a center and a series of departments. And there are pluses and minuses of that, and we've had some discussion about that. And one of the things that came up was how should appointments be made. I know there are a lot of strong opinions, and you guys you have departments, a good number of you, or mostly all of you. So can you just, maybe we can go back and start with some of that discussion. I'll just pick on Rob and get him to start on that. No, that Rob. Yeah, the real sign. How about that Rob?
So how should we organize? Well, let me first of all say I think I think that the temptation in this kind of thing is to sort of advise people to be more like you, right? I mean, we all like, which I'm only going to do partly. So, but I think it is the case there are no examples in the world of stats groups that have thrived for very long without their own department, right? Imperial College maybe in mathematics for a while, but usually when statisticians are in a group with computer scientists only or mathematicians, they haven't done well, and that's because it's a pretty small community, and they're not the most vocal people. So I think it would be important if statistics moves towards, if in the center moves towards being a department. I don't know when that's going to happen, but along the way, you have to get enough critical mass. I think about what would attract my best students to want to come here. What first attract was just MIT, right? It's a world-class organization. But if they came to a place where, the statistics professors are kind of over around campus, and there's no other students around, and there's no PhD students for them, it's not going to be attractive for the best students. They're going to want to go to a place that's already got critical mass. So you have to get enough people in one place, sitting physically in the same place. They see each other every day. There's students around in order to build a good department. And then I think about what's strong about MIT. Well, MIT, the engineering is and computer science is so strong. So one idea might be to move towards a stat and machine learning department, right? Of which there are none in the world, right? CMU is the only machine learning department. Stanford's, we have machine learning across the street, but the relationships are not that close, quite honestly. We have no joint appointments, right? So you guys could become quite novel by starting a statistics machine learning department eventually to take advantage of the world-class computer science that's here and attract top young statisticians who are interested in the computational side of statistics. That's just one idea.
Yeah, I would not go towards stat machine learning. I mean, I think that the focus of statistics is broader than that. I mean, it's all the social sciences and so on. And I think that Munzer's opening dialogue gave a sense of the broader scope just beyond computer science. So I think it's already a given also. Computer science is open to hiring people probably more than any other department. It's just the field changes so quickly. So I think there's just a little more of a Catholic kind of effort there. You're not hearing me? Oh, sorry. Oh, yes. I won't repeat anything. I hope enough my body language was conveyed. But I guess on a slightly related note, I was going through in my mind of some of the faculty that I admired at other universities who couldn't be hired in the current MIT setup. So one name came to mind who's not among the current people here. It was Peter McCulloch, who I saw last week. Peter, if you don't know him, you should know him. If you're not a statistician, you might not. But he's a great statistician. He's developed some of the more influential ideas in the last 30, 40 years. He's not a mathematician per se. Like all of us, he knows a fair amount of math, but he couldn't get hired here in the math department. I think under any reasonable model. He's not a computer scientist. He couldn't get hired. He wouldn't be comfortable in CS here. I can't think of any department in MIT currently where he'd really, I mean, as a young man, he would have been a natural hire and he would have felt comfortable. But he's core statistics, right? So you got a model right now where you can't hire that kind of person. And I don't think that that's a singularity. I think there's many such people and there will continue to be. All statisticians aren't going to be computational or information theorists or so on. So until you can have a core we can hire and the hiring committee is the people in the center who recognize the need for this missing core, and the tenure process allows those people to feel comfortable and flourish, I think you got a broken model.
Susan?
One of the really cool things about statistics is that we can start off in one area of statistics, say we can focus on biology for a while, and then we move to the social sciences. We'll move to political science. We move across different disciplines as our career progresses. So when you put statisticians, when you focus them on joint appointments, you prevent that kind of movement. I mean, some people will move nonetheless, but they have fewer and fewer colleagues.
Yes, one small thought I have. In the private sector, I see people who are actually very thoughtful about how to build organizations. Things like HR does not have much of an impact on universities. I've always ex post thought it'd have tremendous benefits. But having some center of gravity there, because we manage a really large and heterogeneous collection of scientists, and attrition is always a problem. The places that have had the lowest attrition, they feel like there's some center of gravity, like some type of smaller central team. On the flip side, I think it's just absolutely necessary. Otherwise, there's no place to congregate around. But on the flip side, people talk a lot about interdisciplinary work, et cetera. I've always felt like universities, at least the ones I've worked at, have been on the interior of the frontier in terms of making that happen. I'm forced to do it because I have to solve a problem, and it's the people that you sometimes think you have the least to learn from are like the guys you got the most to learn from, and figuring out how to make that process work in the very free, self-directed, decentralized environment of a university is a tough problem.
One of the things that's been so striking to me about this particular symposium is the consistency in the views that have been expressed across all the speakers. And in a certain sense, I think one of the reasons it's felt good is it's kind of been a love fest for the discipline of statistics. And I feel that there's a message there that I'm sure you've been delivering this message over and over, but you can't stop. You have to keep saying there's a discipline here. I think a lot of people, just as mathematicians don't own math, statisticians don't own statistics. A lot of people do statistics. They tend to think because they do it that they know a whole lot about it, which they often don't. And so it's very easy to undervalue it. And I think you kind of have to start with, keep pushing. It's a discipline, you have to have it. It's going to support all these other areas, but unless you have real experts and you have a core somewhere of these people, you're going to run into a lot of problems. And I just want to mention, because you just touched on the cross-disciplinary sides, it seems to me two big things you have to aim for in the university setting. One is being a cross-disciplinary resource, which is to say people throughout the university, they know where to go when they actually recognize they're a little bit stuck. And you have to have enough people. You have to have a critical mass so that that's going to work. And you have to have people in that core who are willing to make the effort to be helpful and maybe get involved in a new field and so forth. That's pushing potentially against some of the other boundaries that already exist disciplinarily for the people who are already here. And then also you need to mount an educational program, because you're going to find that there's a huge demand for statistics. I think it should potentially be coupled with machine learning in some of the education. At the graduate level, I think it would be nice. But for statistics per se, at the undergraduate level and at the graduate level, and again, unless you have a core of people to do this, I don't know how it's going to get done.
Let me just ask a question. Does MIT have the possibility of joint appointments across departments? Yeah. So, and can it be even across your faculties, I guess? But only within the schools?
No. It can be across schools.
Would that be?
It's not often, but it is possible.
Yeah. Because, I mean, I agree with Susan's point that we may want to move. On the other hand, we can also have bases in one department. At least at Berkeley, it's entirely possible to take your position and then move it to another department, and that might be a way to go. So, and also, isn't there already at least one department at MIT which has a broad range of people? I mean, I've heard of the Media Lab, and I guess, is that a department or is it?
So the Media Lab.
Go ahead, the mic. I'm going to use the mic.
Oh, sorry. Yeah. Media Lab is structurally under the School of Architecture.
I see.
And however, they have a similar, so they have hiring capability in terms of slots, but they have to hire the departments. So it's kind of the same structure that the institute will have. But it's a lab, which is confusing about the names of MIT. But it's not a department, but it has slots. Yeah.
But anyway, I guess I agree with all the previous speakers, more or less, in what's needed.
I just added one point about the name and some follow-up to Mike and Rob. I mean, there's a lot in the name. I was at CMU for the fall semester on sabbatical, and some of your colleagues were complaining about the fact that people who want statistical consulting go to the machine learning department. I mean, right? I mean, some come to you guys too, but there's a lot in the name. For some people who want a prediction or classification, they go to machine learning. They don't think about statistics. So having a name, actually, statistics and machine learning, or maybe statistics and data science, would be really an important marketing thing. But it have another effect. If you call yourself statistics and machine learning or statistics and data science, then you have to actually expand your view of statistics, right? You have to know more about computation. You have to teach about distributed computation and databases, which frankly I couldn't teach, but it's an important part of our subject. So we acknowledge the fact that our field is also changing. And if MIT had that as part of their name of statistics and data science, for example, it would grow its view of statistics into something much more modern that a lot of departments in statistics have not done, right? We're still holding on to the 1960s view of statistics. So to look to the future, I think the name is really important, and also the content of the subject along with the name.
Philippe?
For what it's worth, I still don't like the word machine learning. I wish it had never been created, but no. I mean, it wasn't. It was a bunch of computer science, AI faculty at CMU, who didn't really know much about statistics and sort of thought they were creating a brand new field. And the heritage has stayed with AI inside of computer science. That's great, and you're seeing all this work on vision and speech and all that going forward. That's statistics meets. But very implicitly, there was a story about computation. But there's other areas in computer science, including distributed systems and databases, that have nothing to do with AI, and that have a huge impact on the world. And allying that with statistics, I've been working on that for the last 10 years. That to me is a much more powerful combination and where the world is going, and much broader reach. And I like the word, data science is probably a fine umbrella term for that right now. So if I think about one of my database colleagues, he will happily call himself a data scientist. He would never call himself a machine learning person. And so data science is a bigger umbrella that in some sense includes statistics meets databases and distributed systems. And in that spirit, I'm on board with you, Rob. I think machine learning, I think if MIT grabs that word, I just hope they don't. I just don't think that's the right terminology. You got that noted? Thank you.
For what it's worth, in France, we're always late on everything, but it's true.
Yeah, that was a long time ago. Anyway, we had masters of statistics, and we had it was very hard to get any students there, and we changed the name into data science, and all of a sudden the number of students multiplied by 3 or 4 or 5. And so I think data science and statistics is like a really, for the moment, the way it is, it's the best combination.
Are you using the English word, data science?
Yeah,
Maybe
you
that's
have to
what
be
it
English.
is.
I mean, that's the problem. Yeah.
So
but
should we say sciences des
What?
données?
it doesn't work so well.
Sciences des données.
Okay.
So I have maybe a more down-to-earth question. So during both Rob T's talk and Peter's talk, you've praised your younger colleagues, John and Noureddine, respectively. And I don't know, I'm too young to have witnessed exactly what happened in the creation of your, illustrious departments, but I know that, Jerzy Neyman is a name that comes back. Brad Efron is a name that sounds pivotal in the creation of the Stanford Stats Department. And I was wondering, what do you think the importance of having senior colleagues to either support you or inspire you is in the creation of a department? Because here we really are starting from scratch, and it's the 30s right now at MIT, and probably we don't want to wait until post-war to actually be something. And I was wondering if you had any ideas or recommendations on how to expedite the process, I'd say.
But isn't it? I mean, I think we all know that the existence of at least one very forceful leader is essential. I mean, you look at all that we were just talking about, the various success stories, and yes, Neyman was really well respected and successful. Fred Mosteller, was really well respected and very successful, and it seems like you need people like that. You need at least one, and ideally more than one.
No, I think that's right, although I think technically, if you parallel histories, at Stanford, I mean, Brad came, but he's of my generation, really. But you need some, Bowker actually, who then became chancellor at Berkeley, although he himself was not a particularly great scientist, but he had great abilities in attracting and organizing and attracting very good people. So that's really what you want.
I don't really have anything to add. I mean, I agree with you guys. Especially if you have one person who also can get respect from other scientists, right? If it's a very theoretical mathematician who's brilliant, but only 10 people understand what he's done, that's not really as effective. Someone that's well respected and also can communicate with other scientists would be ideal.
So here's the landscape at the moment. Pretty much everybody at MIT is an applied mathematician in some form or another. And we really got a sense of this when we looked at the courses that are statistically related or statistics courses across the different areas. So we have like a new nano center, which is going to be constructed in a few years, where there's going to be probably some very challenging problems in experimental design. We have the Koch Center over here, Cancer, Broad Institute. We have a very active department in Earth and planetary sciences. So we have people in these areas. So what sort of strategies would you all think about for like connecting up these various hubs that already exist, or these spokes that already exist? Because we have all this, we have the makings of perhaps something which could be well beyond what statistics departments are anywhere in the country. How can we take advantage of that? What sorts of suggestions would you offer? Because you've probably, if nothing on this scale, you've probably done something similar, like in your own institutions, in terms of making connections.
I think the crucial thing is really this word hub. I mean, if there is no hub, then the spokes somehow are not really connected. And it strikes me that that kind of fragmentation really leads to some serious difficulties, unless there's an avenue for students to migrate from outer areas to the center and then come back to report what the center is thinking. Then it's the communication is difficult.
And I think Peter emphasized that, I think you used the word transfer in your talk, which I think that's the crucial concept, is that you get ideas transferred from one area to another. This happens, at the level of the whole field, but also happens at the level of a group in an institution. And it's really important. But as far as the structural question you're asking is concerned, I mean, in my limited experience, I think you need individuals who are strongly connected to the areas. I don't know any other way to do it.
Yeah, I mean, I think the hub's important, and in my experience also, it seems that to me it's grad students and postdocs that really are the glue. Like at Stanford, we have a statistics department. We have a lot of applied science departments who come to us with questions, and as a professor, it's hard to learn at our age new things, right? Grad students and postdocs are fearless, right? They'll go into labs with other postdocs. They'll learn about stuff that they're not trained to learn about. And they'll come back and tell me and say, I've got this interesting problem with this guy in biochemistry, and explain it to me in simple terms. And they are really much better than we are at being the glue between statistics and applications. So I think you need a hub. You need a department. Again, I'm saying you need a department with some critical mass sitting in the same place, so they talk to each other every day. And you need students and postdocs. And they're the people that can form the spokes to tie the whole thing together.
Yeah. And just to say, you might come up with some incentive structure for these postdocs, for example, that would just encourage them to take on cross-disciplinary projects and so forth.
Okay.
The NSF ran a thing a few years ago on the future of statistics, and there was a lot of talk about outreach of statistics, and I remember Ian Johnstone at some point deciding that we really needed to talk a little bit more about in-reach, and I think that the crucial thing here is to really try to get that part of the puzzle sorted out.
So do you see like educational programs as being a potential one way of sort of forming the glue? Like I was talking with Mike out there earlier, and Rob had pointed out last night that Mike plans to set up a course for all the Berkeley undergrads in statistics. Is that something we should be thinking about here?
Yeah, as you know well, you believe in it. So, yeah, this is so we haven't gotten to this part of the discussion yet, but one of the reasons for having this hub is that the faculty are incentivized and, in fact, required to teach statistics courses. And that's their full-time commitment. If everybody's adjoint with some other department, the other departments have their needs and their desires, and they say, well, that's not really our kind of stuff, and you can't tell them, well, it's important to my other discipline. And so I am a joint appointment, and CS is somewhat forgiving. I've mainly been able to teach stat courses, using this word machine learning from time to time when I needed to, has suited me. But mainly able to teach that. But not, if you have too many joint appointments, that is a real problem. When I was here at MIT, I couldn't get my students trained in this field. So I would send them to Harvard, or we'd just have textbook reading things, offline. Maybe it's a little better now, but I don't think that much better. And that is a very missing part. When I come and talk to students here across many disciplines, they just have big gaps in their education. So they don't know. So that's the two pieces of this puzzle. But if that's not fixed, then I think a department is kind of the only way to incentivize it. So yes, at Berkeley we are in the fall starting a brand new class that aims eventually, it'll start small, to be statistical inference for everybody. Everyone has been talking for a long time about computing for everybody, and people say that and they kind of believe it, but they don't really want it. They don't want to really invest a lot of their curriculum to just core computer science, because it doesn't really get into their discipline. But statistics for everyone, and they like that, and the two together they really love. So that's how this having a great political impact across the campus. Everyone says a class that does both together, that sounds great. And the cool thing is that you can marry statistics computing and kick out the math and teach at the freshman level. The math implicit, of course, there's the theorems behind the ideas, but it's all resampling, computation, based and non-parametrics and all that. And we're going to try. I'm very optimistic about it, but I think that you can have real-world problems, statistical inference problem, computing and visualization, and no actual math is needed. It's kind of amazing. So I'm pretty sure, but in France, that's a different crowd of. You have to start with the Hilbert space theory, then eventually you can get to the probability, then you get to the statistics.
So
we're
is this
doing
a-
the opposite. We're doing the anti-France model, actually.
So will this be
Yeah.
a course that people will be expected to take primarily as freshmen, or they have to complete before they graduate? Is
No,
that-
Chancellor wants that. We have this new chancellor. He wants the freshman year. Everybody's required to take this. Now that's ridiculous. But it's a nice model to think about. You know, everybody, a philosopher, law student, they should be thinking about data analysis in their own personal lives, if not in their discipline. And they should learn to read the New York Times critically, and so on. And so why not? Why can't we deliver our inferential ideas? They are challenging, but they're not that hard. And if you don't try to do the math, you can convey what it means to do a hypothesis test with resampling and permutation tests. You can convey that with no math, and people can get it, and they can try it on real data, and they can learn to Python program at the same time and do computer science. And I think that I'm real optimistic about this. And so, yeah, you guys should do that here too. I think why not? But you have to find some core faculty who are incentivized. That's their job, and it's not just one person. That's such a big entity. You got to have some collaboration. So again, I think a department is a natural home for that. We're having some structural issues at Berkeley around.
Do you want to
this.
just say a couple sentences? So how many of you are, how many undergraduates do you have, and then how many of you are sort of working on this project?
Yeah, there's 6,000 undergrads per year coming in, so 3,000 per semester, and kind of magically, as you all know, with videos and everything, and you can have a class scale to, it's already been done at 1,500, and so 3,000 is not out of the reach. And we're going to have these little connector class ideas where kind of, extra units that'll get you more into specific disciplines around this core. So I think it's quite possibly scalable to that size. And there's 6 people right now involved in a weekly meeting for 2 hours. They're all just volunteers. And to me, the core is statistics meets computer science for this particular venture. And so it's all statisticians and computer scientists. No, they don't. That's precisely the point. It's amazing how much you can do with just start with some data, make some histograms, talk about the sampling distribution under the bootstrap of, say, distance between histograms, like variation distance between 2 histograms. That's a number. And if I resample the data, I get fluctuations in my histograms. I get fluctuations in my variation distance. And I make an inferential statement now with no probability needed other than a number that 95% of the time it covers, right? At the end of it, I want to do a little Bayesian personal inference with subjective probabilities out of medical decisions. So I want to do some decision tree-like probabilities there. But no sample spaces, no sigma algebras, no nothing. It's really, I think, because you can teach the bootstrap on regression coefficients in this class at the freshman level for real inferential problems. Why not do that instead of wait till you do all the probability and the linear algebra to do the regression and the blah, 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 blah. That's years. So why not just get it right from the beginning?
David?
Thanks. I wanted to follow up on that conversation, but at the PhD level courses. I think it's fair to say that probability is the sister field of statistics at or feel free to disagree with that, but that's my impression, that traditionally you start with probability, then statistics, and so on. These days, when you read most of the papers and publications, it's as much to do with algorithms, computations, and other fields. Do you think that this sister will become a cousin in some future, and that something else will replace that? What do you see in future as sort of fields surrounding the core of statistics in terms of research, PhD programs, and so on?
PhD level is completely different, right? So I was talking about world data analysis and understanding uncertainty and variability, and histograms and box plots kind of start to get you the feel of that, and you can reason with those things. So you are doing probability under the hood, but you don't have to teach them the formals. You don't need to have alphas and betas on the board to start to convey that. But then eventually you turn to probability. Probability, as Peter was, it is the glue of all of this, right? It is the formalism.
Are these beginning undergraduate students?
I was talking about beginning undergraduates. He's now turned the conversation into now, if you want to make them really experts and be really in this field and contribute to it and be serious, yes, you've got to do probabilities pretty soon. So I'm thinking after our freshman course, the next course is as quickly as possible to get into probability. But that's not all students. That's not all 6,000 at that point. Now you're down to maybe the 1,000 or something who are going to get the probability. And
so if students have decided that they want to maybe concentrate in statistics, would they opt out of this, or they still have to take
No,
this?
we believe that they'll get a lot of computing here. They're going to learn to be Python programmers and learn about computing concepts, not just to put code on a piece of paper, but to make higher order functions and think about iteration. So when you do a permutation test, you have to iterate cross numbers and swap them and learn how to do stuff like that. And you have to reason about how much time that's going to take. Oh, is that linear time? So a lot of computing concepts. So both sides are going to get something new out of it. And yeah, there may be a little redundancy, but no, we're thinking that everyone should go through this.
Yeah, I had one thought about PhD students. If you want to talk about cross-fertilization between fields and research, like PhD students, people who are early in their careers, it's far more likely to happen there. I mean, after you've been doing research for 20 years, you're kind of down a path. Some people will go and jump over and pick up something completely new, but that's a fairly low frequency event. I sometimes feel like in some of the PhD programs I've seen in economics, we tend to overprogram people. We jam too many requirements in them within the field. And I remember I got my doctorate in Minnesota, and Leo Hurwitz, it's a much smaller, less prestigious place than MIT, but they produced a bunch of Nobel Prize winners in economics, like Lars. And one of the reasons is Leo Hurwitz said, if you're going to learn math, you don't learn in the economics department, you learn in the math department, because I want you to understand the core underlying principles. And with some of these marriages, encouraging those students to go out and take the courses from people who are truly experts in it, and where they might get shaken up and exposed to something new is a good thing. And we frequently don't allow them the time or liberty to do that.
So yeah, just to add to that, I mean, I think it's a very good idea to have courses like in applied statistics and machine learning, in which students from other departments are in the same class, right? I taught a class with my son, actually, CMU in the fall. It was a reading course, but we required, this was Ryan's aid, that every pair in the project, two students, they had to pair up with a student, like a machine learning student with a stats student, right? So they had to work together, and that was actually a very good idea, because when you're working with a student for 3 or 4 months, all of a sudden you learn sort of how they think, and just having them in the same class, working together, I think really helped both sets of students. So one idea in the graduate level would be to have a course in applied statistics or machine learning, which can grow to be very large. Like the Stanford machine learning course is like 750 students. In statistics, we don't have that big classes, but they've got to be 250. So for a PhD level course in applied statistics, where they used to be like 20, it's amazing. And most of those students are not from statistics, right? They come from biological sciences, from engineering, from business, and they're all in the class together. And that has a great effect on the students. First of all, it forces the professor to communicate the stuff in a different way. Students work with each other. They hear each other's questions. It's a win-win, having courses with students from different areas all together in the same class.
So Rob, in that graduate course that you
Yes.
teach there, so how is it handled sort of topically? What is that applied course, sort of what material you're chiefly covering there?
Well, it's machine learning, it's applied statistics. I mean, things like bootstrapping, lasso, random forest, all that taught. It's not a theoretical class by any means. It's modern tools for big data.
And data analysis.
Yeah.
Right.
So actually, I have a follow-up question on that. So my experience is that when you teach low-level introductory statistics, you end up, if you follow any one of those $160 textbooks, you end up having to do 25 variations on the t-test for population, proportion, or means, or different means. And I think it bores students out of their minds.
Yes.
And I think what's actually making it attractive, what makes machine learning attractive, is that they sort of see magic, right? They have these giant data sets, and suddenly we extract a pattern. And I think actually the opportunity here at MIT is that we don't have this tradition of teaching some more traditional stats courses, but at the same time, we still need to. I think Mike yesterday mentioned teaching layman's book, right? And you're not going to learn how to write a paper tomorrow by reading layman's book. So there's no immediate outcome. I think it's just basics, and it's basic principles. And I don't know if you've thought of it, if you guys thought about how to reconcile learning the basics and at the same time try to enjoy the benefits and how attractive it is to students to have this more multivariate high-dimensional analysis problems where we really extract things that cannot be seen by the naked eye, and not just be bookkeeping for chemist to say, well, I see the phenomenon and I have to go see a statistician so he can tell me the p-value is actually small enough.
Yeah, I think that's a great project. I don't think any of us, we could all give our answers, but I think it's the project of the educational part of our field in the next 10 years to take the core material and liven it up. And partly you make it more computing oriented, but real data oriented and so on. You know, but just even take an A/B test, which, you know, all my friends who go out and work in industry, on day one they arrive, they're asked to do an A/B test. What's that mean? It's just a classical hypothesis test, right? There's two columns of numbers. And t-tests are not, it's not Gaussian data. So they learn maybe about permutation tests or something like that. Well, you know, the layman, in later life, layman put that kind of material into his book. You never teach it because it's late. But you can liven, you can put a real interesting industrial kind of A/B test in a, and then think about what's the error rates, and what if I have not just A/B, I have A, B, C, D, and F, and I look at all pairs, and now you're looking into false discoveries and so on. So I think we can just we have to, as a field, reintegrate our curricula and make it not just you teach the layman book and then you teach a machine learning class. That's just what we're doing now. That's totally suboptimal.
And one additional comment, you know, we tend to focus, when we talk about these issues, we tend to focus too quickly on the content and rather than the goals. And then it degenerates into a bunch of topics, which is actually not, I don't think, as helpful as you know, other ways of thinking about it, which might require you to do something a little more, you know, radical potentially. But if you think about the goals, then a lot of it has to do with the interaction between the, let's call it theory, but the statistical ideas and the data problems. And you really have to think about what are good ways to help students learn about that interaction, because to me that's, again, if we look at the commonality across all the people who talked today and yesterday, that's there and it's jumping out at you. You know, that there's ideas about modeling. I would call it statistical modeling, but you could call it by different names. Probability obviously is the key in there, but how do you get those? How do you get students to come away with that sense that all of us as experts have? And I don't have any good answers, but I think I mean, I try in my own little way, you know, when I teach, but I think part of it has to do with the interaction of problems with the theory that we need.
Peter?
Yeah, no, I think that's a very good point, and I was trying to think, I mean, to some extent, the contrast you drew was, it seems to me, between exploration and validation. Exploration is a lot more fun generally than validation, but you can tie them together, it seems to me, and give an incentive for looking at the validation by you know, spreading a few false things in the data sets that you that you provide the students. Right? They make a few false discoveries, then I think their incentive in looking at the validation techniques is increased.
So I wanted to push this in another direction just for a second. So we've had a little back and forth about statistics, machine learning, and you know, one of the things that, you know, those of us who are statisticians feel good about is there's this theory that we call statistical theory, and it helps guide our thinking about designing methods and analyzing data. And lo and behold, this thing called machine learning has come up, and they've shown us there's this whole class of problems that maybe they can get answers to. I'll put it that way. Is there a way that we could envision having like a unified theory that tries to really link these areas better as opposed to having a tension between them? Is that something which is achievable? Do you guys see that something like that is possible?
I don't see any tension. I mean, the theory of, say, boosting eventually got worked out in the annals of statistics. You know, I mean, the principles are those of statistical decision theory and empirical processes, and there's just no tension. And, you know, now then adding in computational constraints and all creates new problems, but it's not tensions.
Oh, I thought we weren't supposed to.
No, I don't think there's
learning.
on a theoretical level, I think there's no tension. I think machine learning has just been a sociological phenomenon where you brought in this kind of computing, you know, energy into the field. And let's look at exotic new problems. Let's look at matrix completion where almost all the entries are missing. You just won't find that in layman, but it's a natural statistical problem, and you know, you make a low rank assumption and you then prove things using the standard framework. There's no theoretical problem at all, I think. I mean, the theory will evolve, but there's not a conflict. In fact, the early you know, what was called statistical, not machine learning, but statistical learning theory, you know, that was empirical process theory in polynomial time. So it was an attempt to glue a little bit of computer science into a big, broad area of statistics. And then it turned out the in polynomial time wasn't very useful. It was nothing was learnable in polynomial time, and so they threw that out, and now they're in empirical process theory. So I think that it's just you guys are some more. Is this agreeable to some of my theoretically, Philippe and others? Do you think? Yeah.
Well, actually, I don't agree. I mean, in the sense there's no tension. For example, I had Jeff Hinton, who's a good friend of mine, because I was at Toronto. He gave a talk to our lab on deep learning. And frankly, a number of the faculty in the audience they thought it was bogus. I mean, they saw this complicated process that they couldn't understand the detail. I mean, you can understand sort of how it's done, but it's this black box with lots of complicated things. And they thought it was just, black magic and didn't think much of it. But, so there's a tension between, things are very complex, I think. A lot of statisticians sort of, they don't trust it, right? Whereas people in machine learning and CS, they don't mind complexity, and if things work, that's really what matters to them. Whereas statisticians tend to, if they don't understand something theoretically, at some level, we don't trust it.
But that's a sociological comment, right? I mean, the people who work in theory ideas in machine learning will look at the deep nets and try to say, okay, well, there are many local optima here. They must be, you find one of them, and why does it work? And there is an ongoing effort there. It's in the same theory that we're used to. They're not saying, here's some brand new thing out of renormalization group or something that, some brand new theory. I mean, if that happens too, that'd be great. But
So you're saying it's more of a social phenomenon than
to me, it's a social
limitation
phenomenon.
of our field.
When we start talking about a new problem in my group, I have this blend of stat and CS students coming from these two different backgrounds. And often, or in the early days at least, we'll talk about it, and then 3 days later, the CS students have built a program, and they're running on Amazon EC2, and it's, wow, look how great this is. And the stat students will come back and have a theorem that it can't work.
Right.
That's not a tension?
That's a sociological tension.
Okay.
It's not but after 5 years, they all blended up, and they're all kind of get the best of both worlds.
Okay.
Just
Peter?
a minor point, which is that I don't think it's just a sociological tension. It's a tension between min-max and practice. I mean, all the results are min-max results. They're worst case results. And in fact, luckily, what the Einsteins say, God is subtle but not malicious.
You have that same issue in computer science. All the complexity theory is min-max, exponential versus polynomial, and all the practice is different. But it's a field. That's just part of any field where the theory roughly guides you, and hopefully more and more over time. I don't see that as there's not a huge conceptual distinction.
Yeah, just to follow on that, maybe it's not tension necessarily between statistics and machine learning, but there's tension between machine learning and the rest of the fields. I mean, the reality is that if you think about, I mean, we faced this issue as we started the deliberation within MIT. I mean, people in social sciences are very upset at the machine learning people, because the notion that, oh, you just give me data and I'll crunch on it and give you answers, and not necessarily care much about the paradigms of thinking in your field. And I think that sort of sociological or not, it actually has created some of that dynamics.
That's a sign of poor communication skills on our part. I think if we communicate well to people, if we communicate well to people in the other fields, they get it. If we don't, it's the way we speak to people. It's the way we. I think that's a lot of our fault, the data scientists.
Well, and it's also the sociological thing that Mike just alluded to. If you have your 3 computer science graduate students who run away and crunch a bunch of numbers and come to some conclusions, and suddenly they're made public, and they're actually kind of crazy, that's going to cause a problem. And there's lots of instances of that sort of thing. I mean, I would just add that, at Carnegie Mellon, we've had this blend of computer science and statistics for some time now. We do it in a machine learning department. I happen to like it because I've been very comfortable. It's become very comfortable for me. But I would like to say the one place where I find what you might call a tension is if you look at the graduate students that come out of that program, in my estimation, something like 3/4 of them get a pretty good sense of statistical ideas. But there's another chunk of, and I'd say it's like the rest, 20, 25%, who don't really ever seem to get any kind of statistical perspective. And that's dangerous to me and worrisome. And that's something that needs to be worked on. And in some sense, there remains, I think, a tension, in the sense that not everyone who sees themselves as machine learning also has this statistical sense.
So they don't have like a core set of statistics
There,
requirements?
there's a core. There are two requirements. I just don't think they work as well as they should. They have to take a, you know, Bickel-Doxum level, Casella-Berger level course, which is actually a pretty tough course. It's with the statistics students. It's very widely subscribed, not only by these students, but by other departments too. It's probably got well over 100 students in it. Basic theory course. Then they have to do a data analysis project. That, if it were taken sufficiently seriously by everyone, would be, I think, a very good vehicle for them getting good statistical sense. My observation, and I've said this within the department, and we're trying to fix it actually over the summer. We're supposed to meet about this. The problem that I've observed is that some faculty, because of the sociological issues, some faculty who are, computer science, getting the workshop papers out very quickly, having to publish very quickly, they say, I actually had a quote from a very good colleague, who I like very much, but I didn't like what he said. This particular student did this data analysis project, which is now, a couple of semesters potentially, and it really wasn't very good from a data analysis point of view. It was essentially a bunch of theorems and a toy example. And there was a little bit of an exchange, a somewhat heated exchange with the guy who was in charge of the course and had to actually give the credit. And the professor said, look, it was good enough for the Journal of Machine Learning. That was his answer. Machine learning research, JMLR. And to me, that's not a good answer in this situation. So it's a minority, but that would be a good vehicle actually if you did it rigorously. But it requires a change in culture, because that professor has to say, we're not going to get that publication by this vehicle, probably. We can surely publish it somewhere, but it will be potentially a different journal, and it might be a little slower. And there are some. I mean, that's, again, it's sort of a publication sociological tension of a type that has to be faced, I think.
So, actually, staying on the computation question, I have a question specifically for you, Rob. You mentioned this, so the R package, GLMNet, when I teach high-dimensional linear regression, I say just use that one. I know it's fast. It's even easy to understand what's going on under the hood. And I was wondering if at Stanford in particular you have special courses where I think it's actually very important to promote your methods and to have them implemented in practices to have a nice R package. I think probably 60% of statisticians promise to NSF they're going to write R packages of what they're doing. I'm not sure. Maybe Xiaoming can tell me whether they actually do it. But I was wondering if you have a course where you, well, maybe not in Fortran, but is there a course where you actually teach your students how to prepare R packages and how to make them well? I mean, that would be a nice way to actually tie statistics into computation. With
So we have one advanced R course, but it sort of goes well beyond just making packages. Most of it's done by just grad students talking to each other, and it's just done by seat of the pants. But you're right, it's very important, and I think there's also, for example, Steve Boyd has a class on convex optimization. I ask or require all my students to take that class because it's so important to learn optimization. And the stats department doesn't have really any computing classes. So you have to really enforce a good background in computing, optimization, and making packages, writing software. Really important.
Given that everybody's moving towards Python.
Deborah, just use the mic.
Thank you. I mean, given computation is concerned, everybody's moving to Python. I mean, no disrespect to R, but and preparing Python libraries are actually a triviality. So
is extreme what?
Is effectively triviality. I mean, anybody can look it up, and it's like 3 lines of execution. So
Learning.
Yeah.
But to do a good job of it's not going to.
Well, that's a question
matter.
that's a question of teaching computing. For example, what Mike mentioned, which is an ambitious project, is that sort of in one semester class teaching students how to program in Python, and at the same time thinking about data analysis without having the pre-background of probability. And so.
So, go ahead. Go ahead. The mic there.
Carl.
I learned many years ago theoretical statistics and kept waiting to see what the applications would be. And I went to Rand Corporation to learn to do that, and I person I admire the most, I never met him, he died before I got there, his name John Williams. He founded RAND, and he recruited people there who were brilliant. He described his process of trying to find brilliant people and invite them to come out to this new company called RAND in the late 40s. And but the first thing he did was he wanted them to be interdisciplinary. So the seating arrangement was the people, they didn't have departments sitting homogeneously. They had them somewhat scattered. I'm sure it helps to have that. So that would be one thing. And that also fits in with the hub and spoke model, which I really very much like that you folks are mentioning. But as the hub, you have to provide space and an attractive place to bring people in, and then the spoke is all the fields to where they're teaching you what they're doing as you're communicating with them, hopefully to improve their methods. So that's sort of one major theme, and also I think you have to have. I would save some of that money so that everybody doesn't have to be funded all the time doing things, but some people can be. I mean, part of their support is just to deal with the sociology of time, to meet with people in other fields and to bring people together, especially in the early going. Maybe they'll find other directions, but I would find that to be exciting. And the final thing is, one reason I like the name data science is I've seen so many students who are in love with working statistical problems with data. But we start with theory, and somehow that, I think most of you are talking that way anyway. They need to learn some theory for sure, but they also need to just get their hands dirty, because it's pretty exciting to work with real data. It's even more exciting once you know enough to know what problems to look for, and you can invent new things.
I want to add one point. Herschel, are you done, Carl?
Yeah, I could talk forever, but yes, I'm done.
So it's a point I made at dinner last night, but I wanted to say it again, is that, I mean, this is a very cheap hub. I mean, statisticians, besides our salaries, right, we're very cheap. All we need is a little computer, which is a couple $1,000s, not most, right, and our salaries, and a place to sit. The postdoc that I had up on my slide that I work with chemistry, she's going to UT Austin with a $2 million lab, right, to start up. Machines, like, they cost a lot. So, I mean, in talking to deans, where can you get the kind of value to science as statisticians? I mean, we don't cost much, and the value that to scientists across MIT could be enormous just for a salary, really. So it's not like we need expensive labs. We just need a place to sit and a computer.
I was just to come back to what you were saying, Mike, on this teaching at the very first level, numerical statistics, say, before doing math. I think maybe the best way to do it is to do both things together. So you essentially have them work with a data set or whatever, and then build up a bit of theory, so a bit of probability and statistics, and then just do both things together. If you do just dirty work first and then you do the theory afterwards, they don't see the connection. That's my impression.
Well, I just disagree. I mean, I will just disagree. Yeah, maybe there's 10% who eventually want to go into the more mathematical disciplines. Yeah, you do start to move them along that track. They're already there in high school. They probably have already been doing it. But 90% of the people who are going to think about critical data analysis in their real life don't need the theory. They need to use their brain to think about symmetries and permutations. That's using some part of your theoretical brain, but it's not. You got to write down Greek symbols at that point.
You don't have to have a high theory, but it's.
I would just say I think I would agree with you only. I would agree with both of you. That is, I agree with Mike about the first course. Yeah.
Oh, come on, disagree with somebody.
Right. No. I would agree about the first course, but what I think you're saying would apply better to a higher level course. Yes, and because we have a very unfortunate bifurcation in our field of theory and application, and we got to make those come back together.
Yeah, that was Carl's point, I think.
That was Carl's point.
Right, exactly. So guys, is there anything we've missed? Any parting suggestions you want to make to us? Or, question, go ahead.
It was just a thought because there was a notion of keeping pure statistics, even though we sort of more core statistics, even though we moved to a modern statistics department. So I was a statistics undergrad, and we had the yearly reunions, and one thing that to talk with the professor that was managing the undergrad program to talk about what people liked and sort of what worked for them. And so the recurrent thing was that what people seemed that helped them be better thinking as statistician, be helpful when we did the academic consulting, was the design and analysis of experiment classes. So very, very old school, collection of data, design of experiments, presentation of data, with very little inference in that class beyond factorial models and random effects. And it turned out to be one of probably the hardest class in the department. And I would imagine there'd be a danger of wanting to do away with a class like that as obsolete in a department that's trying to be modern. But for me and for people in my program, it was really what made them think as statisticians, and then made them better at inference, and then made them better at tackling modern questions as a statistician. So, yeah, that's what stood out.
Experimental design is having a great resurgence right now.
Right.
Yeah.
So that's a great point. In fact, at Berkeley, we have this core. We have a lot of people, but we still can't find enough people to teach all the classes we should, and we never find someone to teach that class. So we need to hire more people. So in fact, this year we hired Peng Ding from Harvard, a bunch of Harvard people in the room. And we're lucky to bring him in, and he will hopefully teach causal inference and experimental design, two critical areas that we have been teaching at Berkeley. So yeah, if you don't have a 20-odd kind of core-ish people, you're not going to cover these things, which are of huge emphasis to. So one other comment, Moonthor made a comment last night that I thought was really thought-provoking about control theory versus statistics. It's provocative. I'm going to make a comment about it, but I want to return to it for a minute. I was originally, my personal education started in control theory at UCSD, so I took all the classes of control theory, and I still think it's the mother of all disciplines. It has everything in it, dynamics and probabilities and optimization. It's just everything is in it. It's just fantastic. And so in some sense, statistics is nested inside of it, right? The control theory is optimization meets modeling meets the closed loop, and so on. So, but if I think about like just mentally scanning through all the people out there in the world who are kind of technically inclined, who are going to get up tomorrow morning and say, today I got to do a little data analysis, maybe a little experimental design to set up some experiment, or maybe a little regression, or maybe a little this or that. That just feels like a large number of people. And the number of people who get up tomorrow morning saying, I need to design a PID controller today, or to do an H2H infinity design or something like that, is feels orders of magnitude smaller. I mean, this is provocative, I know, but I think that is a little bit the difference, is that you have to have this core that has this, because the interface is so huge. There's so many people that are connected to this discipline. In the current era, I mean, I think, who knows, in 100 years, control theory may be everywhere because we're all this big autonomous, system humming away. That is the vision, I guess. But I think that's not the current state of the world, despite all the beauty of control theory. So I think they are different in that regard. So.
One last small comment for you is technology and engineering institution. I've worked with a lot of your engineers and developers, and the fraction of their lives they spend working with data, I think, is much larger than you appreciate. I mean, data is the fuel that's driving, not only driving a lot of these systems, but there are issues like when you're developing a new system. Show to me in the data why you're focusing on the right problem, or things start to go to hell, and somebody says, drill down to root causes within your system using the data, and you see them struggle quite a bit to be quite candid, because they aren't equipped to deal with those problems. Even just something as simple as measure a growth rate. The prior year, Thanksgiving shifted by a week, and you should have seen people freak out about what's going on with my growth rate, because you can't measure trend and seasonality separately. So there's I think it's just absolutely essential for correctly training your engineers and technologists.
Great. Any other parting comments? Should I turn the floor back over to our distinguished leader here?
say thank you for making my life very easy. So actually, just before we, I think a lot of the comments are extremely valuable to us, and this is exactly what we wanted to get out of this conference, this workshop, sort of your ideas and your views of where the field is going, but more so to be somewhat our advocates for making this succeed. So we hope to keep reaching out to you. I do want to say a few things so that before you leave, you kind of understand where we stand. MIT is committing resources to this. So MIT wants to make this happen. That's a transformation. We didn't have that 3 years ago. Now we have it. And the commitment is happening in space, which is very, very expensive, and it's happening in slots, faculty slots. I mean, regardless of what you say, Rob, a slot is a slot, you know? It doesn't matter what the initial package that comes with it. And that's expensive, and MIT is committing that. The center within the institute that we're putting together is an educational academic center. So courses and programs will be offered through that program. So we are launching a minor in statistics for the undergraduates soon. We will be launching a master's in statistics for all the PhD students at MIT. So that's, you can get certified as a statistician through the master's program. And we're hoping and we're aiming at offering a PhD program when the right number of people are in place. We do not want to offer a PhD program before we have, and that's actually something that we're still continue to debate because we understand the importance of having students and postdocs in the system. So that commitment is there. I think we are already beginning to do a lot of the things that you mentioned, incentivizing postdocs to come in and work across fields, you know, between theoreticians and practical people, and we have funding for doing that. So MIT has come along. And in fact, already, you know, in the past year and a half, we have hired about 5 junior faculty in this area, somewhere in the spectrum between machine learning and statistics. Theoretical statistics, somewhere in that spectrum. And I think if you look at the computational people, you know, with a probability slant, maybe the set is even bigger. So where are we now? I think we have some structural issues within question of how we hire. We've been successful, but we want to continue to hire in those areas. Tenure is going to be critical, but I think we're heavy negotiations with the senior administration to position ourselves strongly to protect all of the junior faculty that we're hiring. And I think there's clearly with this initiative, there's openness to that. And potentially the long-term view of this is becoming a department. But until we have a cohort of people and what I would consider an MIT culture of statistics, I think we're not ready yet to sort of call ourselves a department. And that culture may very well turn out to be different from different places or may mimic some other existing places. We are looking for the fierce senior leader. Feel free to volunteer. You know, and if you don't want to volunteer some of your friends. We are looking for that, so this is happening, and you know, and I think there are the resources that will come with that. So that's kind of my concluding. That as you depart from here, I want you to know that this is a momentum and it's happening, and your help will be greatly appreciated. And I do thank you all for coming in those couple of days and sharing with us your knowledge and and candidly telling us to do things and not do things. Took careful notes of all of this, so I appreciate all of that. I also appreciate the audience for sticking with us for 2 days. This is, I think, I learned a lot. I hope everybody else did. It's been a phenomenal set of lectures and talks that we heard. I also want to thank the staff. I mean, I hate to go through this list, but I mean, they've been amazing, all the work that has been going on, and the food, the accommodations, and the emails, and I really haven't had to do any of this. I mean, it was like people had come up to thank me and say, oh, you know, this is a great organization. I did nothing out of this, so I'm happy to take some credit since I usually get the blame. So take the credit for that. But I think, you know, in particular, you know, Jacqueline and Kevin have done a great job in the pre-organization of this event. So thank you all for coming. Thank you all for sticking with us.